Okay, I think this may be it. We may have lost a couple folks with the link, but we'll go ahead and get started. And I'll introduce Mingyang. He's a postdoc research here at Tennessee Tech, and he's been part of the group for over a year, getting close to 2 years now, working on various projects. First, he was working with the RPE REACH project, and now working on the NASA project. And Ming has a lot of expertise in materials, electrochemistry, and electrochemical background that's been very, very helpful to our program. And as we've been doing some testing, Ming has been doing some characterizing the performance of the SOC and uniquely under pressurization. And so with this, I'll let Ming go ahead and start his presentation. Be about 20 minutes or so, maybe 25 minutes, and then we'll have some questions at the end. So, and thank you all for coming to this month's seminar. And as we continue to do these, we'll continue inviting. So hopefully we don't have any more technical hiccups like this, but thank you all. And go ahead, Ming.
Yep. Thank you, Dr. Roberts. Hi, good morning, everyone. For today's seminar, I have an opportunity to share with you some results we have on the electrochemical impedance study on the pressurization effects on tubular SOFC's solid oxide fuel cells performance and the electrode kinetics. I thank my coworkers Trevor and Jeff for help on the cell testing and the special power sources for providing the fuel cell samples, and Dr. Roberts and the RPE program for funding support. Yep. So first of all, I want to give a short review about the electrochemical impedance spectroscopy technology we use for studying the cell performance. So the EIS has been developed in the field for many years and is very widely applicated for studying the reaction mechanism on the electrochemical cells. So basically, the process starts with input AC signal to the circuit, and due to the presence of various electrical elements in the electrical circuit, the output signal will have a phase angle displacement. So the input and output ratio will be the impedance of the electrical elements and with the phase angle displacement. So for various electrical elements like capacitor, inductor, it will have various forms for the impedance. For the solid oxide fuel cell study, more often than not, we will not encounter ideal capacitive behavior for the electrode. What we usually encountered is a constant phase element with dispersion, with frequency dispersion of the electrical behaviors. As we can see from the logo in this slide from the International Society for the Electrical Impedance Spectroscopy, care had to be taken to interpret the data of the EIS because sometimes the interpretation can be a little bit arbitrary. So should we avoid using the partial interpretation to explain the full mechanism? Next, I want to show you the internal setup of our fuel cell testing facility here at Tennessee Tech. So basically, we have a pressurized chambers for testing a single tube cell, also potentially for testing tube assemblies. So a single tube was fitted into the testing rig, and its anode and cathode was connected to the bus bar for current collections. And these bus bars was connected to the potential stat and all the frequency analyzers for the electrochemical testing systems, and the impedance was tested. For this larger solid oxide fuel cell, as we can see, is the cell has a larger surface area. Here has to be considered because for the potential stat and the frequency analyzer, is a high voltage, a low current tolerance electrical device. In comparison, the solid fuel cell is a low voltage, high current device. So the input signal had to be selected so that a good output signal can be obtained. So the next slide shows the cell we have been testing in Tennessee Tech, and the configurations and microstructure of different cells. So basically, we have tested 9 cells in this test stand. So it's separated into 5 batches. So from batch 1 to batch 5. So each batch has about 2 cells with the same configuration and microstructure, and also thermal processing history. The cell performance, as you can see, is varies from cell to cell, and also the configuration has some variation too. But we can see a trend from the batch 1 to the batch 3, and also beyond to batch 4 and batch 5. That's the still that's the tubular SLC wall thickness is reduced from batch 1 to batch 4 and batch 5. And the tube become lighter, the weight of the tube become lighter. Now we can also see some anode porosity seems to increase a bit from batch 1 to batch 4. So then we test the impedance of this tubular SOSC in our test stand. So first we have to select a suitable equivalent circular model to assign the spectrum we measured to the specific electrode process. So this has been done by a survey of the literatures in the field with a similar cell configuration, electrode materials, and testing conditions. So basically, from a literature survey from the table, we can see that in this study, due to the larger inductance impact from the cables, the thick cable used for the larger cell, we cannot observe high frequency process usually observed, like a charge transfer process on the electrode. Instead, what we observe is a medium frequency process and also low frequency process that is related to the mass transport and electrode reactions. So for the impedance, various ECM electric circuit model are available, but we have to do a systematic investigation about which one is best suited for fitting the spectrum, the EIS spectrum. So we can see from the figure that a 3-element ECM with a medium frequency constant phase element in parallel with a resistor, another low frequency finite diffusion Warburg resistance, and a very low frequency another resistor constant phase element in parallel. That's mostly give the lowest error when we fitting the data compared to other model available. And also is inconsistent with the literatures that this 3-element in the ECM corresponding to some surface to the surface change, gas diffusion, and some like a concentrational conversion resistance for the electrode. After selection of the ECM models, we can study the pressurization impact on the different batch of cells. First, we see the pressurization impact on the batch 1 and batch 2 cells. So we can see that the batch one cell, which is has the largest wall thickness and the most dense structure, has the largest improvement also when the pressure will increase from 1 bar to 4 bar. So we can see from the top left-hand side figures. Also, we can see from the ECM fitting that the 3 elements, the 2 RC and 1 Warburg resistance across all of these 3 elements was reduced as the impact of as function of the pressure. So from this observation, we can see also we compare this pressure impact with the batch 2 cell, which is cell C. We can see that in comparison to the CLA, that CLC showed a relatively less degree of improvement on the similar pressurization conditions. This is assigned to the different cell microstructures and configurations, so that we observe the largest impedance reduction for the cell with the thickest wall. On the right-hand side, we see the behavior of cell in methane field. So in methane field, the pressurization induced the impedance reduction is not as large as in hydrogen. So we can see from the body plot on the bottom of the right-hand side that with the methane, actually, the low frequency or the low frequency peak has shifted to much lower spectrum. Actually, is out of the range selected for the EIS studies. So at this point, the pressure impacts on the very low frequency process cannot be identified. But we can generally see that under the methods, there's a different reaction mechanism at a low frequency, and is not as significantly influenced by the pressure as in hydrogen. Next, we examine the fuel flow rates impact on the cells. So basically, this try to because the pressure seems impact the mass transport phenomena on the electrode, and also the mass transport can be enhanced by increase the fuel flow rate on the anode. So we compare this mass flow rate impacts with the pressurization impact. Actually, we see similar behaviors between a pressure, the impedance reduction brought by pressure increase, and also the impedance reduction brought by the mass flow increase, although to a lesser degree. So we can see that from the left-hand side, which is the batch 1 cell in hydrogen, we see that increased hydrogen mass flow has reduced the cell impedance. Also from the body plot, we can see that the low frequency peaks corresponding frequency has moved to higher values as the mass flow rate increase. Comparatively, the CLC, which is from the batch 2 in hydrogen, also shows similar behaviors. Basically, the cell impedance also reduced by increase of the mass flow, and also the resonance frequency of the low frequency process is shifted to a higher value at higher flow rate. So this phenomena can be explained by the gas conversion impedance from the literature for the larger SOX cells, because for larger cells, there's a concentration gradient along the flow path of the reactant has been discovered previously by the researcher from Denmark. So basically, at the flow rate increase, we see the gas conversion impedance at low frequency will be reduced, and also the peak resonance frequency, according to the equation, will be increased correspondingly. So as we can see from the equations. So this suggests that for certain cell dimensions, a high flow rate may be needed to overcome the gas conversion impedance and keep a good performance for the fuel cell. Also, this flow rate impact is evaluated on the batch 4 and batch 3 cells in the next slide. So we can see that generally the batch 3 cell has repeated what we observed on the batch 1 and the batch 2 cells. There is a certain saturation point beyond which further increase of the mass flow rate will not further reduce the cell impedance. But there is a different behavior for the batch 4 cells, which is the CLE, which is the CLG. Sorry. So comparatively, the CLG from batch 4 shows even a larger degree of improvement at a higher flow rate at 300 SCCM. So this is quite different. So according to our SEM observation, the batch 4 cell has relatively more pore structure, and also in the meantime very similar wall thickness for the tubes. So this can allow a better gas diffusion at a high flow rate and reach the reaction interface. So this can directly contribute to its even better impedance, even smaller impedance values. And also this seal has been proved that it has a high performance. So the next slide, in the next step, we evaluate the partial pressure change of reactant species on the electrokinetics, which is very important to understand the different peaks in the EIS spectrum can be assigned to whether anode-related process or cathode-related process. So we can see that we do the C study on the batch 1 cell B on the different pressures. So we can do a partial pressure change through two different ways. One way is we keep the concentration of the reactant constant, but we increase the pressure. The other way is we keep the pressure constant and we increase the concentration. So both we can achieve the same magnitude of partial pressure change. So and then we can see how the impedance depend on these two different way of partial pressure change. So first of all, we can see on the left-hand side figures, which is we change the hydrogen particle pressures on the anode side. So we see that from the largest arc is at 1 bar with 25% hydrogen on the anode. So when we change the pressure from 1 bar to 2 bar, which is the red triangle arc indicated, there's like a 50%, almost 50% reduction of the impedance we can see from the spectrum. Meanwhile, if we do the similar, we keep the pressure the same, and we increase the concentration of the hydrogen. We double the concentration of the hydrogen, like shown by the blue dots, the blue dots in the spectrum. We don't see as much change of the impedance as we increase the pressures. So this is indicative that the anode related process is more dynamically driven by a pressure change of the hydrogen. On the other hand, we can compare to the cell's behavior on the right-hand side on the cathode. So on the cathode, we also keep initially low oxygen concentration. Like we can see that in the biggest arc, which is has the lowest concentration of oxygen at the lowest pressure, which is 1 bar. So comparatively, if we increase the pressure from 1 bar to 2 bar, as indicated by the red triangles arc, that we see a slightly reduction of the impedance on the cathode side. But if we increase the concentration of the oxygen but keep the pressure the same, we see like shown by the blue dots. We see a larger improvement, like double the reduction of comparatively to the pressure increase. So this shows relatively different behaviors for the cathode. So it's more driven by the concentration or chemical potential of the oxygen than by the pressure. So we also extended this study on the batch 5 cell. It's a more recent test. So this batch 5 cell, which is a CLI, we can see that it shows very similar behaviors to the cell B, which is a batch 1 cell. Despite they have very different microstructure and configurations. So this shows that this different behavior on anode cathode can be a little bit independent of cell characteristics. So we also see that when we on the anode side, when we increase pressure, there's a larger impedance reduction than we vary the concentration. While on the cathode side, on the right-hand side, similar behavior for the a different behavior for the cathode have been observed that increased concentration is more effective to reduce the impedance than increase the pressure. In the middle figure is the body is the both plots of this cell. So we can see that in the body plots that actually when we when we reduce the hydrogen concentration on the anode, we see a peak increase because impedance increase. And also we see the low frequency. This is the low frequency arc related process. So we see this arc shifted to a higher frequency value when the hydrogen concentration is low. On the other hand, if we reduce the oxygen concentration on the cathode side, we didn't see we see the arc increase, the magnitude increase, but we don't see the frequency shift for the cathode side. So this shows that there's this low frequency process can be from a different kinetic process related to anode and cathode, and they may convoluted together, showing the spectrum. So the current ECM study may overlook the contributions on the low frequency process. Yeah. So the last slide is just a summary of what we have observed and found during this period of time on the tubular SFC on the pressurizations. First, we observed the pressurization can improve tubular SFC electrokinetics through enhancing the mass transfer related process, especially at the low frequency. And this is also we can achieve similar effects by increasing the mass flow rates. Also, we can see that pressurization improvement depends to a large degree on the cell configuration and the microstructure, like the wall thickness and porosities. So further, we have verified that the impedance change due to the reactant particle pressure change is different between anode and cathode. The anode is more driven dynamically by the pressure change, while the cathode is more dominated by the concentrational gradient or the chemical potential of the oxygen. At this point, we can see that, especially for the low frequency process, this can be the ECM fitting maybe not conclusive. So a further study will be needed to refine the current ECM and verify the kinetic process identification. Analysis like a distribution of relaxation time can be utilized to further separate the peaks in the spectrum. So basically, it is assumed there's a probability distribution functions of the polarization resistance across the different frequency domain. So this is what we're going to do in the next step. And also, I think we have to do more comparative studies on the same batch cells with the similar configurations, so the results can be more consistent. And also to further differentiate anode and cathode electrode mechanism, we can do some electrode infiltrations with the catalyst, so we can see it's a relative impact on different electrodes. Thank you very much for your attention. That's my presentation. Thank you.
Does anyone have any questions?
Ming, this is David Nesbitt. I'm a mechanical engineer, so forgive me. This is something I'm learning about this particular technology. Is there something that drives the maximum pressure that you could operate these fuel cells at?
Yeah, that's a very good question. I think currently we are limited to 4 bar. I think the pressure, because at high pressure we began to see some temperature gradient along the tubes. It is usually due to the fluid field impact or due to some sealant leakage. So we are limited to at 4 bar right now.
That's our testing capability right now too.
Okay. Thank you.
Yeah, as our testing capability, and yeah, it's more open in the sense as far as flows. So we don't know. There needs to be some thermal fluid analysis, I would say, to carry out to see, because as you go higher in pressure, your sensitivity of flow distribution gets higher and higher because the density changes.
Right. Thank you. Good job.
I think Dr. Lvovich has a question.
Yeah, thank you. I actually have a few questions.
Yes.
Question number one is, can you go back to your experimental setup? Because it's my understanding that you use 2 reference electrodes, right?
Yeah, it's actually it's just it's 2 electrode measurement. It's so the cathode is working, and the anode is also the reference.
Oh, I see. So, okay. Oh, okay, I see. So it's essentially 2 electrode measurement. Okay. So, next question is, you had essentially 2 peaks in the border plot, and let's call one of them low frequency and the other one is medium frequency, although that medium frequency is about 10 hertz, give or take, not really very medium. And this one seemed to be not affected by pressure changes or by essentially by rate of supply of gases. What is your assignment for that first peak? You had a model, earlier literature models versus your own interpretation, like in one of the previous slides, and and I seem to miss it. So that RC medium frequency, what physical process does it correspond to, in your opinion?
Yeah. I think the intermediate frequency impedance it's like if we vary the concentration of the partial pressure of the reactant, these should have a different exponential dependence, the impedance with the concentration or the partial pressure of the reactant. So for diffusion related process like vapor diffusion, it should have like a close to 0.5 exponential dependence with the partial pressure of the reactant.
Yeah, no. I understand that. RC1. What is RC1?
You mean the CPE one?
Yeah.
Yeah. So it's assigned to the surface exchange of the
Surface expansion.
yeah.
Okay.
Yeah.
Yeah, that seemed to be reasonable to me, because it's it's not even very significantly affected by by pressure, by concentration. It is probably affected a little bit, but sort of almost on a superficial level. But what my last question is, for your low frequency, when I look at your low frequency profile, it's actually, I mean, you have all the data. You looked at that, I'm sure, before for all those plots, but but for some of them which are more prominent, I would even say that alpha is very close to 1. And and your conclusion obviously is correct, that there are at least 2 processes hiding there. At
Yes.
least 2 kinetic processes hiding there, but but alpha is very close to 1, which actually also tells us that that RC constant for those 2 processes is probably very close to one another. So not only it's at least 2 of them, but but their characteristic frequency is probably very close also to one another.
Yes, I agree with you, sir. I think that's the case. I think yeah, I think maybe some like a DRT analysis can clearly separate the peaks. Yeah.
That's why. But that's why I started asking you a question about reference electrodes, because it's obviously it's not easy to find reference electrode for that system. You know, anything more sophisticated than just a piece of platinum, but but that's that might actually help you to look more closely into kinetic processes and separate what's going on cathode and what's going on the anode.
Yes, sir. Yeah, I agree with you. I think ideally it would be great if we have some like a half seal studies, like an annual half seal and cathode half seal.
Yeah,
Then yeah. But
All
at
right,
this
well,
point,
thank you. Very
yeah,
good.
thank you.
Hey, Ming, this is Ted Orn.
Yeah, thank you. Yeah.
Nice package of work here you put together, really well presented. A couple of questions. Was all the data done at OCB? And did you attempt to do any DC bias on this?
Yeah, I think most of the data are all collected at OCB. The best one has sometimes give some very like scattered data. So yeah, I think I plan to do some at least quite like a lower level of current, like 10 amps, if we have the booster fixed.
Okay. Yeah, I'd be curious if any future testing to maybe try some of that, because I know sometimes that can really give some different indications, in terms of the performance, if you can get it at a more elevated current density. So on the fact that the cathode is sensitive to concentration rather than pressure, concentration of oxygen rather than partial pressure of oxygen. What's your interpretation of what that is telling us?
Yeah, a good question. Yeah, I think it looks like the pressure is more dynamically, it's more mass transport related. So for the cathode, it means the rate limiting step is probably, although I know cathode seems to have a pre-condensed structure, but it's very thin. I think it's more indicative of like a reaction, electron surface reaction rate limited process.
Yeah, okay, that was what I was thinking as well, that maybe it's a oxygen reduction reaction or something along those lines. That's the rate limiting step.
Yes, yeah, I agree with you.
Yeah. With the mass or the mass flow rate effect on the anode surprises me a little bit. Do you think so? If this is all taken at OCB, I wouldn't expect that would be a fuel utilization effect. I guess seeing that we don't have a lot of exchange going on, we're not reacting a lot of fuel. I just have a hard time getting my head around why that would be such a big player. That's not really a question, I guess.
Yeah. Yeah,
I guess I
think,
kind of have a question on top of that. Do you think it could be some sort of like fuel crossover or leakage that kind of gets silenced as you have more fuel?
Yeah, that's a good question.
Right. Yeah, I think definitely. I think we can double check on that. I think for some cells, a high flow rate do seems important for cell to have a good performance. For some cells, like yeah.
How would you try to test for that leakage? Could this be done with like a GC? If you are able to see some like water in the cathode stream, you're getting some fuel leakage.
Yeah, I think it's EVs can be picked up by the EIS from the RT analysis, and definitely we could we could try to identify that. I would just have maybe have a better seal and make sure we have a better seal each time we load seal, and we can, if we from the same batch, we should be able to tell that. Yeah.
Yeah, I think one way to maybe tease that out, if you changed your total flow rate by adding nitrogen, keeping the hydrogen, flow the same, that might be able to be a way you could tease out whether it's something that's consuming hydrogen like a leakage, or if it's an actual mass transport effect on the surface.
Well, that's kind of the study that I think we've done here. We keep the hydrogen flow the same and just adjust the nitrogen flow and dilute it, and that's how Ming is changing the concentration and partial pressure.
Oh, right. Yeah.
So maybe it is baked into the data here as to why the anode and cathode might be behaving differently. Could be due to this leakage. Just need a way to confirm that.
There is concern about this. We have tried on different cells. So I think if there's a leakage, there could contribute a little bit, but looks like there is a shifting of the frequency. Looks like it's due to the different cell with different configuration and microstructure show similar behaviors. And also the cell some cell has showed good performance. I think yeah.
Well, is there, I guess if any other questions come up, feel free to reach out to myself or Ming. Don't know if you had your contact information here, but you can reach out to me and I can get in contact with Ming or the appropriate person, and we will be doing more testing soon. We're starting more testing on this as we're gathering more information, and hopefully we'll be publishing pretty soon on some of this information. But thank you everyone for attending, and apologize for the technical difficulties in the beginning. But yeah, so we got them solved, and thank you for participating, and we'll have another one actually pretty soon, in the next, I think, few weeks, if we get to one in December. We're planning on one in December, so I'll send out an email as I do normally, announcing that one, and then we'll have another one the following month in January. So thank you all. Have a good Thanksgiving next week. I hope to see you again soon.
Thank you very much.
Good job.
Thanks, everyone.
Good job, Ming.
Thank you.